Okay, everyone. Good evening. We start. My name is Alex. Some of you guys have seen me in the exercise sessions. I'm going to step in for Ryder today. He's out of town traveling. It's going to be an easy lecture tonight, so no big equations and stuff. We're going to talk about system development and the value of bond graph modeling. Some of you guys might have asked yourself, what is this bond graph stuff all about? Why do we have to learn that? And why is it important? And yeah, I guess today's lecture is going to answer that, hopefully. That's it. So if I ask you guys whether you can model one of these systems with the knowledge you have gained so far, what would you say? The one on the left-hand side here is an aircraft heating and ventilation system. I mean, every one of you, I guess, has sat in an aircraft and has realized these little ventilation things on top of your seat. And yeah, it's a fairly complicated system, right? On the right-hand side, we have a energy or power transmission system. An electric car, where you basically have to decide where power has to go. How much power does the engine see, the transmission back and forth. And on the bottom right-hand side, we have some mechanical gear system, which may be less complex than the other two because it's just a mechanical system. There is no fluid, there is no electric power. However, it's still a large system, quite some gears, interactions between mechanical parts. So what would you say? Could you model one of these systems? Well, I guess not too many raised their hands. So what's the thing with these systems? How do they differ from the ones you have had in the lectures or in the exercises so far? Any ideas? Come on, it's late, but it's not that late. I mean, you have modeled mechanical systems, right? The one on the bottom right-hand side. But where's the difference between this one and the mechanical examples you have seen? Well, let's make an example here. Come on. If I ask you, is this a system? Would you say yes or no? It's a system. Yeah, absolutely. Is this a system? It's the chassis and the drivetrain of this Porsche. Yes, no? Yeah, system. And this one, it's the engine, basically. Just the engine, nothing else. System as well, or not? No? Yes. And this one here, it's a piston, basically. Nothing else. Single part. Is it a system? No? So please raise your hand if you think that this is not a system. 1, 2. Yeah? Okay. Maybe 50% think that this is not a system. The other 50% would consider this a system. Well, what is the definition of a system? And then we get back to the first slide. a system, as you might remember from the first lecture, is basically a bunch of elements having some relations with each other and serving a higher purpose. There is an environment, everything which is not part of the system, which is outside of that control surface, and everything which is inside that control surface is a system. So this is a very generic definition, right? You can basically apply it to anything. This lecture room is a system, or you guys are elements of that system, including myself. There may be some relations between some of you, maybe not between all of you. So everything is a system, and this piston there is a system as well. Because even though it's just a single part, it has certain features which you could consider to be elements, right? There's these rims, there's that big bore, the diameter could be considered an element, and there's a logical relationship between all these elements, right? You have to have a certain diameter to fit into the cylinder, and the diameter of these rims has to be a little bit smaller. So there's a relationship between these elements, and this piston is a system as well. So the bottom line is, system is a scalable term. You can basically treat everything as a system. It just pretty much depends on where you put this control surface, what is the boundary of the system, what you consider to be part of the system, what you consider to be not part of the system. But obviously, these four examples here are very different systems. So I guess if we take this piston example here and we just let it fall on the bottom, it probably will bounce off a little bit, a tiny little bit. Probably not because that thing has too much of a spring or a compliance, rather because the bottom bit probably has some sort of compliance, but nevertheless that pretty much is one of these examples you have seen in the exercises, right? Simple mass spring damper system. So I guess most of you would feel confident to model this piston falling on the ground with bond graphs, as you have done in the exercises or in the with various examples. The engine is a different story. It has a lot more parts, meaning it has a lot more elements, or you could say it has a lot more subsystems, a lot more components. And there are considerably more relationships between these elements. And the same goes for the drivetrain. And yet again, the car is another system on an even higher level than the other three. So that means this one here, all of these are systems. However, they are systems which are sort of out of reach for you guys for the time being, because it's probably not an easy task to model such an heating and ventilation system of an aircraft using the bond graph methodology as you have applied it so far. I guess most of you would agree. Yeah, today we're going to see how we can actually model this stuff here. Complex, large systems using bond graphs. Okay. Some of you may have seen this already. It's a methodology, an abstract concept of how to develop systems, but especially large and complex systems. It's called the VModel. It originates from software engineering, and it's fairly helpful as a guideline, as a template. First of all, if you need to develop such an aircraft heat and ventilation system, or better to say the car, maybe an easier example, you need some requirements. That means you basically ask yourself, or someone else asks you, I want this car to be fast, I want this car to be nice, good looking, cheap, good acceleration behavior, no consumption at all. So all these things make up requirements which in general are contradictory. They do not fit together, meaning that, for instance, a good acceleration behavior, meaning from 0 to 100 in whatever, 1 second, normally doesn't fit to a low weight, right? The more mass you have, the more mass you have to accelerate. But anyway, first of all, before you develop a system, and this is regardless of the size of the system, so it also applies to the piston example we have just seen. You need to ask, what is this system supposed to do? How is it supposed to look like? What are the requirements? There is, besides bond graph and behavior, performance modeling, which you guys have done so far, meaning you, for instance, have investigated the acceleration behavior. Can it accelerate within a certain time to a certain value? There is another way of modeling large systems, which is called, or which basically investigates the operational scenarios. For instance, using MATLAB or equation, which means that in most cases you neglect something, right? You neglect many effects actually. You always only consider the most important effects, or the effects which you think are most important for the system's performance behavior. That one-wheel bike, for instance, the spring itself has some damping feature, right? If that damper wasn't there explicitly in the exercise task, in order to make it really correct, you would still have to account for some damping of that mechanical spring, because the spring itself will dissipate some energy when it moves. But this is something which you usually neglect, so you model idealized physical systems. Once you have that model in place, you derive that bond graph model as you have done it, which is straightforward if you have a simple mass spring damper system, which is a little bit more difficult if the system gets more complex, and which is not an easy job if you want to do this for a car, for instance. Once you have the bond graph model in place, you basically start to develop the equations from the bond graph, which again is nice and straightforward if you have a mass spring damper system. I guess most of you know the solution already. But again, it's not as easy if you have a lot of bonds, if you have a lot of elements, a lot of masses, or a lot of inertias, basically a lot of resistances, a lot of compliances. And think of relationships in terms of bonds and nodes and junctions. A lot of junctions mean a lot of complexity in the bond graph, and consequently in the mathematical model. But once you're there, once you have the equations in place, you basically start to implement the equations in a certain tool. So far you guys have been using MATLAB in this course, but I mean in theory or in practical, MATLAB is just the choice of the course. Basically you could use any other tool, for instance Excel, or Simulink for those of you who have worked with this tool. But as shown on this slide, these tools basically only do the simulation job, meaning you implement the equations, you assign some parameters, the mass is 80 kilos, the simulation time is 10 seconds, and then you press the button and you get a nice result, which basically is what you're looking for. However, you have to do quite some steps prior to this in order to get to this simulation result. And ideally, especially if it comes to large systems, we can get rid of some of these steps here, right? Because you don't want to really mess around with equations on that aircraft system level or on that car system level. In fact, there are some tools which enable you to do bond graph modeling and then provide the equations as a result of the bond graph model. That means you don't have to go through the bond graph manually and decide, okay, here I have this node and then this is the C element, okay, I start to develop the equation at this point and so on and so forth. You basically have your bond graph modeled with one of these tools. You press the button, you get an equation, you press the button, assign some parameters and start the simulation and get a result. That's quite cool. But again, if you think of that car, doing this step from having an idealized physical model and develop a bond graph from that on that car system level is still quite a task. So as you might have guessed, there are tools which actually allow to model the physical system as you have seen it with physical system elements such as a mass, a spring, a damper in the mechanical world, or a resistor and an inductance in the electrical world, or a fluid resistance in the fluid world. So you make use of these elements and model the system, which basically is, as an engineer or as a scientist, is not that complicated, right? Because you know that if there is a long beam and there's a force acting in the end or on the end, and that beam is connected to the wall, you basically know that, okay, there is some compliance in some springiness in this beam. It will deform, but there's also some mechanical resistance, so to say, which dissipates energy. So that task is actually not too complicated. Do this first step here, derive that idealized physical model. And this is what we're going to do today. We're going to work with one of these tools and basically model some of the examples you have seen so far so that you can see the difference between the way you guys have worked so far, doing it from scratch, the hard way, and making use of one of these tools in order to model more complex systems. So to wrap up the first part here, for those of you who have heard fluid mechanics and have worked with fluid simulation tools or also structural mechanics, you may, some of these names here may be familiar. ANSYS, for instance, is a vendor of Fluent or CFX, two very important two big simulation tools for fluid dynamics. They also provide a mechanical solution. OpenFOAM is an example for both structural and fluid mechanics. And there are others. All these tools allow to model on a very high quality level in the sense that they take into account 3 physical dimensions. So in order to model this piston, for instance, you really would take a CAD geometry, would transfer that to one of these tools, for instance, apply a certain force, a certain pressure, some heat flux, and then model whatever happens in this piston, right? If you think of the car and all the physics involved in the car, for instance, when it accelerates, it is actually not possible with today's computational power to use these systems or these simulation tools, to model such complex systems, because you would have to take most of the elements into account, a lot of relationships between these elements, a lot of physics, and that just exceeds the available computational power still. Which is why we deal with bond graphs or system simulation. Usually we do not take into account 3 spatial dimensions. We just think in 1 spatial dimension. For instance, these fluid problems you guys have worked with, it's just the x coordinate of the pipe, which you really consider in the model. But you usually don't mess around with the y and z coordinate, right? There's no information regarding the spatial solution. It's just in one dimension, basically. The normal way to work with 1D simulation, one-dimensional approaches, or not the normal, but a conventional way would be to use Simulink, for instance. Some of you may have heard of Simulink, which is basically a tool where you model the differential equations. And it's highly used by cybernetics people or control engineering. But the problem there is that you basically, as mentioned, you model the differential equation, which is why it's called causal modeling. There's a specific relationship between the variable you're looking for and your input variable and something which represents the system. And the problem here is that once you have modeled the equation as you see it on the board, you cannot really do anything with that model anymore. It's sort of hard-coded. And another concept which is based on bond graphs is called acausal modeling, which basically means that here we do not really assign something to something else. We rather model something which is really an equation, in the sense that if you think of bond graphs and what you have learned about causality, that you can't really say that y is the consequence of the right-hand side. It could also be the other way around, meaning that the right-hand side is the consequence of y. And all these system simulation tools basically make use of that concept, that which is the essential, one of the essential things about bond graphs, that unless you really specify a certain source somewhere, the underlying equations of that bond graph are of this sort. Equations and bond graph methodologies, you couldn't really investigate how a use case of a car driver and a car would really look like. For instance, if you get into the car, you need to, maybe not in the future, but for the time being, most of you guys still use a key to open the door. So there's some interaction between the key and the door. Then you open the door, then you sit in. These are different steps, right? The user, meaning the car driver, needs to undertake. And these different steps obviously yield in some requirements for the car. And one way to model this and to deal with all these interactions and the different process steps is to investigate these operational scenarios by something which is called SysML, System Modeling Language. It originates from software engineering as well. And it basically enables you to do these types of modeling, which is not really part of this course, but if you go for big systems, it is an essential additional modeling task that you will have to consider. Then we have system simulation, as this course is termed. It basically represents what you guys have done so far, maybe on a not so large scale, but nevertheless. It's the interaction of a system with its environment, the internal performance of a system and the system components. And if you want to model, or if you want to develop, better to say, a large complex system like this car, on this level you might investigate this acceleration behavior, which is given as an example up there, right? A certain acceleration performance that you want to achieve, and then as a consequence of that, or as a result, you know that the car can't be heavier than, I don't know, 1 ton maybe, which then imposes certain requirements on the subsystems of that car, meaning the sum of all the subsystems cannot be larger than 1 ton, right? So by utilizing system simulation, you not only model the performance of the car, you also understand what the individual components of that system have to look like, or what performance requirements you need to impose on these elements, on these subsystems, which then helps the guys who actually develop the components, the engine, for instance, or the internals of the engine, to do their work, because all the technical requirements you impose on these guys will then be an input on that lowest level here, which is basically the development or the design of the individual subsystems and components. Some of you may have worked with CFD in order to simulate fluid systems, three-dimensional computational fluid dynamics. But there's also other examples such as structural mechanics, if you want to investigate the deformation of that piston due to heat or force and pressure acting on this piston, then you will utilize some structural computational approach. And nowadays, and I think the car is a good example, you will also have to consider electronics and cybernetics, but also software, right? Because that car is actually a multidisciplinary or multi-physical problem. It also has electronical components which interact with your mechanical parts, which also interact with the fluid system, the lubrication system, for instance. And all that basically needs to be arranged in a certain manner to yield the requirements which are imposed on the highest level. Once you have a certain component in place, for instance this engine here, you can actually make use of the system simulation work which you have performed on the left-hand side there. Imagine that you have a working system simulation environment in place which represents the car basically, and you could investigate this acceleration behavior. Now if you have this engine in place as a physical object, you can actually test this engine embedded in the system simulation environment, which is called Hardwareinloop Testing. And you can then basically make a verify whether this engine suits the or fits the purpose, whether it fulfills the requirements or not. And finally, we have the final product as the end of this process. This is what you're looking for. And as you see, system simulation is just one element of the whole development cycle. just as well as other simulation approaches, as you may have seen it before in other engineering disciplines, such as fluid dynamics, CFD, or structural mechanics. Today we're going to dig a little bit into the system simulation box there. There's one thing which is important to keep in mind. This VModel is a logical view on the process of system development, which means that you shouldn't misinterpret this as this process, which I've just briefly explained, as something which really happens over time. Obviously, you cannot just write down all the requirements and then you nicely, one step after another, end up with the car in the end. Because as you guys know from your exercise sessions or from anything else in life, you always need to test something. In most cases it doesn't work, and then you start all over again. So this is just a conceptual logical model, and really over time you basically iterate. Just with anything else, you perform one of these V's, realize, okay, that car isn't really doing the job, so we need to do a second cycle and a third and a fourth. This is something which you really have to keep in mind, because it is very important to actually not specify too much in the first place, but rather write down some requirements, get started, check things out, and then eventually see whether it works or not. So if we take these elements here, or these examples, and arrange it in a certain manner, that they reflect both the amount of relationships, but also the amount of elements. One could do this, for instance, in the way depicted here. Obviously, the car has the highest amount of elements, but also the highest amount of relationships between these elements. And the piston has the least amount of relationships and the least amount of elements. Basically one, if you have a mechanical view on that, right? It's just one part, but there may be more logical elements within this piston system, as mentioned before. And a simple concept how to determine the complexity of a system is actually the amount of elements and the amount of relationships, right? The more elements, the more relationships between these elements, the more complex a system is. So basically, one could, in a simplified manner, describe the complexity of a system with these two indicators. And now if you think about these examples from the first slide again, the aircraft ventilation heating system, the electric car and the power system in there. I guess most of these systems are on the top right hand side of that diagram, right? And in order to model these systems with the system simulation as we have, or as you have used it so far, we need to make use of different tools. You're not going to get far if you want to do this with MATLAB and good thinking and equations. This is basically what you have done so far, right? You have had a physical system as an input, meaning the conceptual sketch of, for instance, a mass spring damper system. You remember this one-wheel bike exercise I think the input there was really a figure how this bike is supposed to look like. There's one guy sitting on the bike, and there's a spring and hydraulic damper. So that's basically the input one usually has if you want to model a system. The next step is to basically translate this into an idealized physical model. You don't know what is the consequence unless you specify a certain flow and start to develop your causalities. We shall see an example later on. So all these tools in the green box are examples of system simulation tools which are based on bond graphs. And as mentioned, you don't really model the bond graphs. It's rather that you model the physical system. But since it's based on bond graphs, it pretty much helps when you know what bond graphs is and how you develop a bond graph from a physical system and how you develop an equation from a bond graph. I guess the Mercedes here is a tool which is called LMS, AIMSIM, which is commercialized by Siemens, I guess. But it's also fairly expensive, and which is why we stick with the MathWorks world and use Simscape, an additional environment in the MATLAB Simscape Simulink family of products, which is based on bond graphs. And we'll do two examples now using Simscape. Two examples which you know, a mass spring damper system and the one-wheel bike. And then we can compare that to the way you have done those examples. And in the second part of the lecture, you guys basically play around with Simscape yourself. I hope most of you, or I guess most of you, have brought their laptops and have a working MATLAB installation with Simscape. And as you shall see, it's pretty straightforward. So you can basically take one of these exercise number 4 examples, which you should have implemented in MATLAB, and try to model this using Simscape, and then compare it with your MATLAB solution. That's going to be the task for the second part of this exercise. But for now, we're going to do 2 examples with Simscape. Are there any questions so far? Yes, so MATLAB as you know it, I think I posted that on its learning. You basically start up Simscape by typing in Simscape, and eventually there's something coming up. For those of you who have used Simulink so far, you can also use press this button here. Can you guys see that? Yes, this button here is Simulink, right? Which basically leads to the same environment within MATLAB, which is required to make use of Simscape. So Simscape comes with a bunch of libraries. We have foundation and utility libraries, which basically contain quite some stuff in order to model quite some systems. You find dampers in there, spring elements in there. You find fluid resistances in there, pipes, for instance, or nozzles. Also sources, flow sources, effort sources. This is everything is contained in these standard libraries. But there are also dedicated libraries to the different physical domains. There are dedicated libraries to mechanical drive trains, the one which is called driveline, or electronics, fluids, and so on. So in order to make use of Simscape, we just create a new model here. And well, it is helpful to use this library browser, which contains all the elements, all the libraries and all the elements one can make use of. For those of you who have worked with Simulink, you know this part up here, right? You might have seen some of the other toolboxes that come with an academic full license set. And down here, you find Simscape. As just mentioned, different libraries for different purposes. The examples of today can be modeled by the basic libraries almost purely. This foundation library here contains quite a bunch of different physical disciplines. If we want to model a mechanical mass spring damper system, we just see the mechanical library here, where we find in the translational elements box, or in the translational elements folder, we find different mechanical elements such as a mass and a spring and a damper. This is straightforward. You basically drag and drop the stuff you need into this environment here on the right-hand side. For some reason, it's a bit slow on my computer, but anyway, you just drag what you need and arrange that in a certain manner. So remember that term, physical modeling, as opposed to bond graph modeling, that level of modeling which is based on bond graphs and the modeling of bond graphs. Here we model the physical system, meaning that we arrange this in a certain manner to represent our system. You can rotate these things with the Control R or something equivalent on a Mac, and then arrange that it represents something like a mass spring damper system. We also need some reference, some wall, for instance, in the mechanical world. And then you basically just connect these elements in order to represent that system that you want to model. Now, how does this work internally? If you double click on one of these blocks here, you see some parameters that you can assign. For instance, here we have this damper, so there's a damping coefficient which you can assign to this damper. And internally, each block has a set of equations. So in all cases, you can basically, or you should be able to actually see the source code of the block. Meaning you should be able to see the equations implemented in a certain MATLAB similar language. And by the way, you can also amend these blocks to suit your needs. So if that damper, as we have it now, is not really representing the physics of the damper you want to model, you can basically start to play around with these with this code here. But anyway, as you see, we have certain sections here, and the most important one, we don't get into the details now, but the most important one is this one here, equations. This is the physical equation which represents this damper, and as you see, there is this this double equal sign, which basically means that for this tool and for also for any of the other tools shown on this one slide, it is not the case that f in this case is a consequence of the right hand side, unless you start to specify, as we shall do in a second, a certain flow source or a certain effort source somewhere in your system. Until then, this equation could also be flipped around, or it could be rearranged, manipulated such that it yields V equals F divided by D. And in fact, this is something which is being done in this tool internally. So once you have modeled this system physically, as we have started now here, and once you have finished this job and press the button, this tool actually, or all these tools actually take this model, this physical model, and derive bond graphs and equations from that and rearrange the equations in such a manner that it's solvable and that it provides the solution that you're looking for. You remember that one-wheel bike, there was this first case where someone jumped on the bike. So the input for that system was some mass that in a step sort of appeared on the top of the bike. But there was also this second case where the bottom was moving, which is a nice example of how the very same system will lead to two totally different equations, right? Because in the first case, you specify the mass to be there instantly, and you're looking for that position which changes over time. Whereas in the second case, the bottom moves, which is a total different system input. Okay, so now we have this simple system here in place. Now we want to impose some signal, some force on that. Simscape itself is based on bond graphs and on physical on flows of physical things such as energy and effort and flow. In order to tell this system, here's some force coming in, we need to make use of some Simulink elements. So one thing here is, for instance, under sources, there is a constant. We take it simple. That constant is g times a mass, and this constant needs to be translated sort of needs to be translated to a signal which can then be used in this Simscape environment. It needs to be translated from a Simulink system, from a Simulink signal to a physical signal, PS, which is the job of this block here. Now the last thing we need basically is, 1 second please, is an ideal force source, which is now equivalent to specifying some effort source in your bond graph model. We input this physical signal here. And I guess this is more correct. And this one is being connected to this Mars. A little bit more nice, you can, yeah. And then we also have one of these. On the other end. Now we need some physical values. I guess the mass in the one-wheel bike was something like 80. Spring 8,000 Newton per meter, and damper, I don't know, 400 maybe. To finalize, we need a block which is called solver configuration. Don't ask me why. This is basically needed in every Simscape model. This may be different in other tools. It basically tells the solver some stuff. And finally, before we can get started here, an important setting to take is in the settings, there is this topic Simscape, and in here it helps to specify that the simulation data is supposed to be logged, everything, and that it's supposed to open a viewer after the simulation. So that's everything we need. I hope that works fine now. If we press the button, you see, you could just see on the right-hand side that it was compiling, meaning that it translates this physical model into a bond graph and derives equations, potentially differential algebraic equations, and then solves it, this system of equations. And this here is this viewer we just set in the preferences. And if we now take a look at the spring, translational spring, at the R end of the spring, which is the rod, the other one is the case, but this is just terminology basically. There we have the x over time, meaning the position over time, the change in position over time, and this, I guess, pretty much looks like the result of that one-wheel bike. This viewer here enables you to actually take a look at everything, so you can take a look at all the different results of the different elements of the system, which in this simple case are pretty much equivalent, but which in a more complex case will certainly be of help to investigate the different elements. So for instance, the velocity of the mass should be equal to the velocity, or well, vice versa, to the velocity of that spring. You can also access these results using MATLAB. There should be something like this here in your workspace now, which is called SimLog. It contains all these results which we can view in this viewer in a structured sort of structure, MATLAB structure. So you can also use conventional MATLAB plots and other post-processing approaches to visualize your simulation results. So as you saw, it's fairly easy and straightforward. Any questions? Please.
Can you show again how you define the constant?
The constant, yes. So this this Simscape world basically is just about energy, pressure, effort and flows. And in order to create some signal, meaning telling this ideal force source what it's supposed to do over time, we need something from Simulink, which you find at the very top of this library browser. I think this constant is also found in commonly used blocks, but it belongs to, I think, sources. So within sources, you find this constant box, but you should also find it in commonly used blocks. Within sources, you also find something which is called signal builder, which is quite nice because you can specify a profile there. For instance, you remember this one-wheel bike exercise with this step where you had to create some complex function in MATLAB to make that work. Now with this signal builder, you can just basically define that signal and off you go. But anyway, you take this constant, plug it, put it into your model. So it shows up here. And since this is a signal, it comes from this world. So it cannot readily be interpreted by Simscape, which is based on this concept. So this is why you need this converter, which you find in the Simscape world again, in the Simscape library. Here we have the Simscape library. Oh, sorry. We have the Simscape library here. And this should be under utilities. There you find these converters, both ways, right? From Simulink to PS, which stands for physical signal, and vice versa. Any other questions?
The value, how different?
Oh, you just double click on it. So you have this mask, and this is equal for all these blocks, both for blocks from the Simulink and from the Simscape world. And here it's just this constant. So you basically specify a constant value, which is now in this example g times the mass of the system. I'm sorry, times the mass of the mass in this system.
Then you have to change the mass here. Everything you change the mass in the mass.
Well, you could also do something like this. You can basically write in input. Then you create a MATLAB script where you define input equals 9.81 times the mass, meaning that you don't have to specify numerical values in these blocks. You can specify variable names and then use a MATLAB script to assign numerical values to all these parameters, which makes it much easier, obviously, when you have larger systems. Any other questions? Yep.
Again, how you got the output graphs from that?
The output box, this viewer, if you ensure in that particular model that you're working with, if you ensure that you select in the settings, which is this button here, this one, if you ensure there that in the Simscape topic on the left-hand side, that you basically log all the simulation data and then open the viewer after simulation. If you specify it like this, then this viewer will pop up automatically, and you can browse through all the different results. This one here, workspace variable name, this is the variable name under which all the results will show up in a MATLAB structure in the workspace once the simulation is finished. It's this one here. This shows up after the simulation. And you can also basically go through the simulation results within MATLAB. This is it's called node, not structure. However, it's similar. So you can basically go through these elements using MATLAB as well and access all these values from within MATLAB. Any other questions? Okay, then let's take a break. And in the second part, you guys can then try to model one of your exercise number 4 systems. And I'll be there to help with issues. Okay? You may remember these group projects, and unless you decide for something yourself, there's also stuff we offer. So, as mentioned on one of the slides, it was mentioned that there are actually tools which enable you to model the bond graph and then produce the equations from that bond graph. One of these tools is called CaliBond. It's the example on the left-hand side here. That was developed in the mid-90s, I guess. However, it was implemented in MATLAB version 4 or something equivalent, and it doesn't work anymore. So if anyone of you guys is really into MATLAB and coding and a bit nerdy, this is a nice group project to make this tool work again, and then show with some examples that it works again, and benchmark it with some exercise results, for instance. And the second group project we can offer is model a wind turbine drivetrain. It's a special wind turbine where the drivetrain consists of a fluid system, meaning that the energy basically is transferred from the wind turbine to the frequency converter and to the electrical grid input by use of a fluid transmission system. So it's quite some physical domains in that wind turbine system, and there one could use, for instance, Simscape to model this. But you may also, as Raida mentioned, you may also use come up with own ideas, and you may also use Simscape to do these group projects. Okay, now we take a break.